Okay, welcome back. Where we just left off, we are reversing a hard-coded string. And so to finish this off, we're going to accept an argument and then reverse that. So we're going to start off with a printf. What is that? No, I don't want that. Please enter the string you would like reversed. Line break, semicolon. I then need to, I haven't done this in a while, so scanf, so const, what is all this stuff? I don't understand this prefill stuff, and I need to get rid of that stuff. So the scanf, I don't really remember how to do that. How do I take that again? Blah, 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 blah. Okay, and then in the guessing game I did scanf, that is the number. Okay, so it's just a straight up scanf with a substitution. So I'll say it's a percentage. I think it's an S, right? And it's interesting because percentage S, I have a note that says it takes a character pointer, but you can't take a pointer when you're taking an argument, right? So I guess it does some magic jujitsu here and actually takes a string of, I don't know. And how did I do that? Guess number. I guess I have to declare it first. So, character, user entered. And then I have to use user entered. And what is this and again? Oh gosh, yeah, it takes in something and puts it in the address of user entered. I swear these stars and these and signs killing me. Actually, should this be an array? No, it doesn't allow me to do that. Okay, so now let's just printf. User has entered string percentage %s, user entered, and then, ooh, okay. Let's comment out those calls. See if this can output something that we can use, just so I can see what's happening here. So ABC, all right. User has entered string ABC, so I'm on the right track here. So now let's uncomment this, and we need to use and here for user entered, and then we're going to printf the result. A string, and we need a new line there. I always forget. Let's compile that again, run it, and theoretically, that reversed it. I believe we have succeeded. Please review my code and tell me if it satisfies the lesson. The fourth step in our plan. Okay. I wonder if it's it doesn't know where to look. Okay. Let's give it that. Please review this against point 4 in our plan. All right, we've got a serious bug in main that step 4 is specifically designed to teach you about. Fantastic. Okay. Look at string reverser 30 to 31. So this uses a single byte on the stack, room for exactly one character. Well, yes, that's because I tried to do this, but it didn't let me. Room for exactly one character. Then this happily writes hello 6 bytes into that 1 byte slot. The other 5 bytes spill into whatever's next on the stack. This is a stack buffer overflow. It's classic undefined behavior. It might appear to work because the compiler probably padded the stack frame, but you're corrupting memory. So I'm messing up the stack, really. If the input were longer 200 characters, you'd smash the return address and crash or worse. Okay. So it says, verdict against step 4, the reverse function itself satisfies the requirement, but main has a memory safety bug. That's exactly the kind of thing this phase is meant to surface. So I guess this lesson is working as intended. Learn by doing. Context, your reverse function is correct. The bug is in main. Your task, fix the buffer declaration and the scanf call inside main. Sizing the buffer. You need an array, not a single character. Yep. I tried to do that, but it said it didn't give me an option because I'm guessing it needs a size. Otherwise, it doesn't know how much memory to allocate. And I am still working on conceptualizing this idea that everything takes memory because I'm just so used to all the abstractions that have been built up in modern programming, right? It needs to know how much memory to give it. So pick a size that's big enough. So you just guess 256, I guess. Can you put it in here? Does that work? I don't know if that's correct, actually. The AND in scanf, once user entered is an array, do you still need the AND? Recall that arrays in C decay to pointers when passed to functions. So because this is passed to a function, scanf, it's automatically decayed to the pointer at the start of the memory. Well, is there a pointer? Because it's on the stack. I don't know. Recall that pointers, the array name itself already evaluates to a character pointing at the first element. Well, let's take this one at a time, all right? 256. I don't think this is the right syntax here. Is this the right syntax? Yes, that is the right syntax, so I guessed correctly. Breakdown, okay. The size must be known at compile time. That's what we're learning now. The array name decays to a pointer. When you write user entered in most expressions, the compiler treats it as this. Okay. Okay, okay, I have a question though with the array decay. Aren't we using the stack when we declare the user entered array? So is it writing to memory itself or is it writing to the stack? The two idea, okay. The array lives in the stack. That's what I'm saying. That's what I'm saying, dude. When the compiler sees this, it reserves 256 contiguous bytes in the current stack frame. So it's not in the memory system that we're looking at. Decay is about the type system, not about where the memory lives. What does that even mean? When you use the name user entered in an expression, the compiler converts that expression's type from character 256 to character pointer, where the pointer's value is the address of the first element which is still on the stack. So it works whether it's on memory or on the stack. So decay is a type conversion at the expression level. The bytes don't go anywhere. The pointer the compiler hands to scanf literally points to the same stack memory you just reserved. Okay. Stack versus heap is about lifetime and allocation. Arrow versus pointer is about type and what the compiler knows. So let me get this right. So, like, I could choose to write this to memory using star or something, right? But the fact that I haven't means it's on the stack, which makes sense because it's temporary. However, the way the stack works mirrors the way memory works. It's just more accessible to the CPU. Is that correct? It's going to take me a while to get understanding about all this memory stuff. Okay, so it says I've got the right direction on most of this, but a couple of the details need cleaning up. Let me pull them apart. Claim number 1, I could choose to write this to memory using star. Okay, but it's almost, but the star isn't what puts things on the heap. Star is just a pointer. You can have pointers to stack memory too. Oh, so this would also be on the stack. What puts memory on the heap is malloc. So we haven't done any of that yet. So the distinction is who allocated it, not whether you use this. Local variable stack, malloc is heap. Claim 2, the fact that I haven't used means it's on the stack, which makes sense because it's temporary. Right conclusion, slightly wrong reason. It's on the stack because you declared it as a local variable inside a function, and your stack allocated things are temporary in a very specific sense. They live exactly as long as the function call that declared them. When main returns, oh, that's cool. Yeah, because, yeah, okay, cool. Whenever the function that calls them returns, the bytes are reclaimed. So claim 3, the way the stack works mirrors the way memory works. It's just more accessible to the CPU. Here's where the model needs a correction. The stack is memory. Yeah, it's not a separate thing that mirrors memory. It's just a region of the same RAM that the heap, your code, and everything else live in. The same DRAM chips, same address space. What makes it fast is a combination of 3 things. 1, allocation is one CPU instruction. When a function is called, the compiler emits something like, okay, this is assembly code, right? Subtract RSP 256, literally subtract 256 from the stack pointer register. Subtract 256 from the stack pointer register. I guess the register is like how much it has total. So no bookkeeping, no free list reversal, no metadata. malloc has to do real work. The stack just moves a pointer. Okay. Not completely understanding that, but let's move on. The CPU has a dedicated register for it. Okay, RSP, the stack pointer register on x86 and 64 chips, always points to the top of the stack. This isn't a special channel to memory, it's just that the CPU was designed with stack operations in mind. Instructions like push, pop, call, and Brett all implicitly use the stack pointer register, the RSP, register stack pointer. So stack ops compile to fewer smaller instructions than equivalent heap ops. Then cache locality, this is the big one. The stack frame for the current function is almost always already in the CPU's L1 cache. That is the fastest, the smallest cache. Why? Because you just touched it. Heap memory from malloc could be anywhere in RAM. Possibly scattered, possibly cold, not in cache. Okay. So what I wanted to do is now look into the previous exercises I've done. So they've all been doing stuff in memory on the stack. So everything that I've done so far has been on the stack. Okay. I guess that leads the question, like, let's see this. Yes, okay, so they are all have been on the stack. Your programs have been using more memory regions than the stack the whole time. You just didn't have to think about it. Okay, let me walk through what each program touches. Project 1. Okay, let's open that up. argc, argv, stack, locals, parameters. Okay, hello world, please subscribe. Read only data segment, not the stack. Okay, that's cool. argvi strings themselves. So the character pointer, argvi, the strings set up by the OS at process launch in a special region near the top of the stack. Printf itself is a code segment of the library C linked at runtime. Okay. Whatever. Okay. 2. Temperature. The Fahrenheit temp, that's on the stack. Okay. So I've declared that on the stack. Scan result, stack. Celsius temp, stack. The enter Fahrenheit thing is a read-only data segment. Gotcha. 3, guessing game. Goal number. So these are all stacks. All right, this is on the stack. All the format strings, read-only data segment. Okay, I get that. And then these are codes. Okay, cool. No project has used the heap yet. That's coming in project 5. Well, I hope this has been insightful. It's probably been really frustrating for those of you who actually know C and you just find me struggling with these concepts. But we'll get there. We'll get there. So today we've learned a little bit about how the stack works, the fact that it's on L1 cache. Okay. Let's move on and actually fix this, right? Okay. Okay, sweet. Let's move on and finish. I'm getting warnings. So 31 has a warning. Format specifies wrong. So I'm guessing we don't need that because of array decay. Because if I'm looking at this anyway, then this is redundant because it decays to a pointer at the start of the 256 buffer size. But why is there a problem? That's what I want to know. So this wants a character pointer. We're giving it a pointer to an array of 256 characters. Those two types point to the same address in memory, but they're different types, and the compiler is right to complain. I don't understand. Those two types point to the same address in memory. Okay. I understand the solution is to drop the ampersand, but why is it a different type? User entered in an expression, array to pointer decay kicks in. So that's the fixed version. It decays to a character pointer. Which is this? Okay, it's explicitly got the index 0. When I'm using the ampersand, I'm explicitly asking for the address of the array as a whole. I didn't even know the entire array has an address. The decay rule is suppressed when AND is applied to an array name. Type becomes character, a pointer to an array of 256 characters. Isn't that what this is? Both produce the same numeric address, the start of the array, but the types are different and the compiler tracks them differently. User entered type is a pointer to a character, the address of a character. And user entered pointed to the first character. And user entered without the index pointed to the entire array. The third is a different type even though the bits are identical. So this is a real type that's occasionally useful. It's a type you'd want if you were passing a 2D array around and wanted to preserve the row size. All right, I'm at the point where I don't care anymore. But it's interesting that it did that. And so now let's compile. Let's run again. Blah, blah, blah. Blah, blah, blah. Okay. Final review, please. I'm excited to stop messing around with this stuff and start getting into more advanced things. But I guess you have to understand fundamentals before you move onwards. All right, we can move on to step 5 with good conscience. Oh, okay. It is saying that there's an error, there's a problem with scanf here. It's still unbounded. The buffer is now 256 bytes, but %s will happily write past the end if the user types more. Address sanitizer would catch it. Okay, so scanf is actually not going to necessarily respect the 256 stack size, right? To fix, tell scanf the max width. Oh, and so you can actually tell it the max width here. So it's 255 because you've reserved 1 for the end rune here, this 0 thing. Okay. The width specifier is the C idiom for trust the input but verify it fits. Okay. What is this? String length. Not worth. Okay. There's just a lot. There's a lot that I just don't know. But I want to test what happens. What I want to test now, right, is what happens when I give it a string that's longer than 256. Blah, 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 blah. What do you do there? And is it going to crash my computer? It's stuck. It's not doing anything. I'm going to Control C. Okay. I just entered a string that is more than 256 characters. It just hung. What happened? What happened? Please tell me, Claude, what happened? I wonder how much training data it has on C and people asking it ridiculous questions like this. Because I think I have an ADHD learning style or something. I don't have ADHD as far as I know, but I really just want to know things. I think it's stuck. I think we've, oh. Okay, so we've hit the terminal's line input limit, most common cause. When you're in the blah, 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 your typing isn't sent to the program, one at a size. Okay. So our program, because it's given it this entire thing at the same time, we've overloaded the kernel side line buffer. Okay. So it just sits there forever because it doesn't accept the thing. Okay. Okay, so scenario B, if I typed between 257 and 1024 characters, the overflow happened and weird things ensued. That would have happened if this was slightly smaller. What would it have done? It would have written past the end of the buffer, trampling whatever was next on the stack. Oh, okay. The brutal truth, the C standard doesn't say what happens. It just doesn't know. Okay, but I did this after putting in scanf blah blah blah. What's the point in declaring the max size if it's not going to respect it? What is the point? Maybe it was giving an answer. What? Okay. That is being respected, but at a different layer than the one that's hanging you. 2 different limits, 2 different places. Okay. Are you gonna let me scroll here, dude? Oh, you're gonna automatically scroll me back. Okay, you're gonna automatically scroll me back. This controls only the last hop. Scanf your buffer. It doesn't. It says no matter how much the input is on standard in, I'll only write at most 255 characters into user entered. That contract is being honored. If you typed 600 characters and pressed enter, scanf would read all 600 out of standard in, but only write 255 into your buffer. No overflow. But I hung upstream of scanf. Okay, fine. Yeah, all right. So give me a string of 300 characters. I'm gonna test it. Yep, I'm gonna do that. Let's run it again. Boom. And it reversed up to E. So I gave it this, and then it gave me this. Okay, so that's what it is. So it's only done it up to 255 characters, I guess. Yeah, so expected output 255 characters reversed. So yeah, that works. So if it even gets to this point, if I haven't like completely flooded the max whatever it is, then yeah, it is actually going to just use the first 255. Excellent. Well, happy with that. Sorry if this is annoying. My learning style might be chaotic. But next time, we will be moving on to dynamic arrays. What is that? No idea. Oh, implement a growable array. Okay, so the new concepts, finally we're getting to the heap. malloc, realloc, free, heap versus stack, size of. I guess I've already been interrogating it with heap versus stack stuff. I might try next lesson to ask it to prepare a lesson with like sort of steps that I can break down, that it can break down for me instead of me just fumbling about and then asking it questions. But we'll see. Thanks for watching. Please like and subscribe.